Greetings and welcome. This is Dr. BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the time period of simple pendulum when hanging from the ceiling of a lift, gain or loss of oscillations due to change in acceleration due to gravity and length of the pendulum. The course outcome of this session would be compute the time period and frequencies of simple compound and torsional pendulums using the basics of free and forced vibrations. Topic covered would be time period of simple pendulum when hanging from the ceiling of a lift, gain or loss of oscillations due to the change in acceleration due to gravity and length of the simple pendulum. The topic learning outcome would be understand the concepts of free and forced vibrations with simple harmonic motion and apply them to field problems. Now let us see the condition where the simple pendulum has been fixed to a ceiling of a lift, where the ceiling of the lift, the pendulum will be moving up and down, right? Though as the pendulum is fixed to the ceiling of the lift will be moving up and down, and along with the lift, the total pendulum will be moving up and down. So first case what we are considering is lift is moving up. When lift is moving up, the inertia force is additive to any load. As we can say that, hence we can write F is equal to mg sin theta plus m into a sin theta. And from this, if we simplify the equation, we can write MA, which is written for the value of F here, is equal to M sin theta into G plus A. And A can be written as sin theta into G plus A, where M and M from LHS and RHS gets cancelled. So it can be written as A is equal to sin theta into G plus A. Therefore, time period T can be written as T is equal to 2 pi under root L by G plus A. Where in the previous simple pendulum condition we have seen where A is equal to sin theta into G. So here in place of G we are applying G plus A, where the A value is in addition to the acceleration due to gravity, and this is the equation for the time period of simple pendulum when the lift is moving upwards. And when lift is moving down, what happens is the time period T can be written as the similar case when we consider here, we can write it as T is equal to 2 pi under root L by G minus A. That means the acceleration is being subtracted from the acceleration due to gravity. So these are the equations of time period when the simple pendulum is hanging through the ceiling of the lift and the lift moves up and down. Now, if we consider the applications of simple pendulum here, there are two important terms that we need to understand. One is beat, where it is defined as half of the oscillation. It is also called as swing, right? Half of the oscillation. We have already studied that oscillation is complete to and fro motion, right? Oscillation is complete to and fro motion. That means from this point, complete movement of the object to the maximum extent and again coming back to reach this maximum extent, this complete movement, complete one vibration is called as the oscillation. So now considering the half of the oscillation, nothing but one movement from this position to here, this is termed as the beat. So half of the oscillation, or else from this position to the maximum this extent, this is termed as the beat. So in this way, half oscillation is termed as the beat. So this is one of the application of simple pendulum where beat is defined as half of the oscillation, and it is also called as swing. And time period for one beat in case of simple pendulum. Okay, so for one beat, nothing but half of the oscillation. What would be the time period in case of simple pendulum? It can be obtained as pi under root L by G. That is T is equal to pi under root L by G. Then coming to seconds pendulum. Seconds pendulum is different from the simple pendulum where the pendulum which executes one beat per second is called seconds pendulum. That means, as we have discussed here, for traveling from this maximum extent to this maximum extent, okay, this one beat, for one beat, if it takes 1 second of time, for one beat, if it takes 1 second of time, nothing but for half oscillation, if it takes 1 second of time, then it is called as the seconds pendulum. Then it is called as the seconds pendulum. Now coming to time period. For time period of the seconds pendulum, if we consider, what would be the value of time period of seconds pendulum? It would be 2 seconds, right? Why? The time period is the time taken for complete oscillation. Okay, so to and fro motion. For one complete oscillation, the time period is being defined. So time period can be stated as the time taken for one complete oscillation. And for this seconds pendulum, the time period would be 2 seconds. As for one beat or one two motion, it is taking 1 second. So for two to and fro motion, it will take 2 seconds. Okay, so that is the case where the time period of simple pendulum or the seconds pendulum, time period of seconds pendulum would be 2 seconds. Thus, the time period for seconds pendulum is equal to 2 seconds. Now let us go to the topic for gain or loss of oscillations due to change in acceleration due to gravity and length of the simple pendulum. So let us first understand what is this concept all about. Change in acceleration due to gravity. As we know, on this earth, the acceleration due to gravity is not same at all places. There is a small difference between the acceleration due to gravity for different hemispheres and different locations of the earth. Okay, so for the same pendulum, when it is at one position, at one acceleration due to gravity position, it will have or it will execute some sort of time period, and other position it will execute other sort of time period, because the time period is dependent. Simple pendulum's time period is dependent on the acceleration due to gravity as well as the length of the pendulum. As in the same case, for the same location, if the length of the simple pendulum changes, then also as per our time period equation, the time period will change. So now let us see what happens with the change in the G and L. We know that time period for one beat is equal to pi under root L by G. Then for time period of n beats, we can write it as n into pi under root L by G. That is, T is equal to n pi under root L by G. Okay, so time period is n pi under root L by G. So from this we can write n is equal to T by pi under root G by L. Now taking log on both sides, we can write log n is equal to log T minus log pi plus 1 by 2 log G minus log L. Then differentiating this, we can write dn by n is equal to 1 by 2 dg by g minus dl by l. Since t and pi are constants, we can consider if L is constant, dn by n is equal to dg by 2g. That means there is no difference in L, the length of the pendulum. Then we can write the equation as dn by n is equal to dg by 2g, where dl, which is the difference of the length of the pendulum, is not happening, that is 0. Hence, we can strike it off. Then for if g is constant, then what happens? dn by n is equal to minus dl by 2l. How these two are applying? If L is constant, this term is becoming 0. Okay, and if g is constant, dg is becoming 0. Acceleration due to gravity is constant, nothing but the change is not happening in the location, then acceleration due to gravity will be constant. Okay, so then we can take the equation dn by n is equal to minus dl by 2l. In this way, if g and l gets changed, then the values will be changed. The negative sign indicates that increase in the value of dn by n decreases the value of dl by l. That is the consideration which we need to take. From the above equations, give the time gain or loss that a pendulum undergoes on account of change in length or change in gravity due to shift in location. So this is about the applications of simple pendulum and the gaining and losing of the time because of the change in position or location. This concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.